Okay, so remember that we have several different names, different equivalent names. So we have fx, a polynomial function. A polynomial function, then it has zeros, real zeros. Real zeros means fc is equal to 0, then c is a real 0. Or of course c is a real number. And we also have a polynomial function equal to 0, like a polynomial expression equal to 0, then it has a solution. Solution also means fc is equal to 0. So solution is a different name for real 0. Okay? With real or without, it's not important. So solution is 0. 0 is a solution. So sometimes if they ask you to find the real solution, find the real solution of the polynomial equation 5 to x to 5 minus 5x to 4 plus 12x cubed minus 24x squared plus 32x minus 16 equal to 0. They ask you to find the real solution. Technically, they ask you to find the real 0 of the polynomial function. So remember that we have to factor it. This was the practice, the example in the last, this was a function in the last example. So it can be factored as what? As this, x minus 1 times x minus 2 squared times x squared plus 4 equal to 0. And still you can have x equal to 1, x equal to 2 solutions. Okay? So to find the real solution is to find real 0. There's no difference. And you still go through those steps. You find that this is a integer coefficient polynomials. So you find the potential list of the list of the potential rational solutions, and you try one by one. Once you figure out one, you use syntactic division or you use a long division to reduce the degree, and then you repeat that process. If you have a higher degree, if your polynomial has higher degree, it possibly will take long time. Okay? Okay, so this is a different name, just a different name. A real 0, a real solution. You do the same job. And in this computation, let's check here. Ax squared plus bx plus c. Sometimes it has a real solution, sometimes it does not have. For example, 1b squared minus 4ac, the discriminant is less than 0, has no real solution, or has no real 0. If it has no real solution or no real 0, it cannot be factored as a product of a 2. It cannot be factored as the product of 2 linear polynomial functions. So if the discriminant is negative, then this quadratic polynomial cannot be factored as a product of 2 linear polynomials. In this case, we call it irreducible. What is irreducible? If you cannot break it, if you cannot factor it, it's called irreducible. Okay? And then we have a theorem. The theorem says every polynomial function, every polynomial function with a real coefficient can be uniquely factored into a product of linear factors and or irreducible quadratic factors. Okay, so every polynomial will be the product of those factors. Okay, and if you only have irreducible quadratic factors, for example, if you have fx equal to x squared plus 1 times x squared plus 4, something like this, then this function has no real solution. It has no real solutions or real zeros. It's a bad case, but this bad case has some property. You see here, this is a degree 2, so the degree of f is 4, so the degree is even. And what happens if the degree is odd? That's next theorem. A polynomial function of odd degree that has real coefficients has at least one real zeros. At least one real zero. Why? You see here, you have odd degree, then you may have some irreducible quadratic factor. It is even. You have another one possibly. It's the degree is still even, but it's the total degree is odd. So definitely you will contain one linear factor. This is because the function, the polynomial function, must contain one linear factor. Linear factor will give you solution 0. Linear factor will give you a 0. So that's why we need odd, because a quadratic polynomial always has a even degrees. Odd means you will have linear factor. Okay, so that's the theorem. That is the theorem. Okay, let's see the next. Let's see the next. We will see how we use them later. So in this part, we introduce the words irreducible polynomial. Irreducible polynomial just means you cannot break it. Irreducible is always a quadratic. Quadratic is irreducible. Okay, it's a discriminant less than 0. And then every polynomial can be factored as a product of such stuffs. It's the real coefficients. You can always do that. And if you have an odd degree, it has at least one real 0. Okay? Okay? Then next, let's talk about some restriction about the zeros. bounds on zeros. There's a theorem. The theorem says it is about the bounds on zeros. Let F denote a polynomial function whose leading coefficient is 1. Okay, so fx is equal to x to n. The leading coefficient an is 1, so you don't see it. And an minus 1, xn minus 1, a1 x and plus a0. So that's the only condition for the polynomial. The leading coefficient is 1. A bound m on the real zeros of f is the smaller of the two numbers. Okay, so we have two numbers. One is that the max of 1 with ups value of a0 plus ups value of a1 plus ups value of an minus 1. This is one value, and the other value is 1 plus max ups value of a0, ups value of a1, ups value of an minus 1. Okay? So here, this theorem, there's two things I want to explain. What is a bound? Bound means a number m is a bound on the zeros of a polynomial if every zeros lies between negative m and positive m. So basically it says the following. You have negative m here, positive m here. All the zeros will be between them. Then these two, this m is called the bound. Okay? On the number line, if it hold the interval negative m, positive m covers all possible zeros for this polynomial, this m is a bound for this polynomial. Okay? For the zeros of this polynomial. That's a bound. And max, the other concept is about a max. Max AB just means you pick up the larger number among A and B. If you have more terms, for example, you have a max A, B, C, D, E, whatever, so it will be the largest number among them, among the set A, B, C, D, E. Okay, so for example, max 0, 1 is equal to 1. Max 3.14 and the pi is equal to pi. Okay, so that's what max means. You just pick up, you have two numbers, you compare them, you select the large number. Okay. Okay, so that's the theorem. Theorem says if you want a bound, this can be a bound. And one more thing, the bound is not unique. If this domain, if this interval covers all the zeros, then you make bigger one. You also cover all possible solutions. So the bound is not unique. This is one of the choice. Okay, so for example, find a bound on the real zeros of each polynomial function. Okay. A, the polynomial function f(x) is x to 5 plus 3x cubed minus 9x squared and plus 5. Okay, so let's just follow the definition. So first, this theorem can be applied if you have leading coefficient of 1. Okay, so now you have leading coefficient 1. Very good. And then you just compute the max between 1 and the ops value of each coefficient, except 1. There's no 1. You see here, we only consider a0 up to an minus 1 ops values. You don't consider 1. 1 is not in that. So you have 5. Absolute value of negative 9 is 9. Absolute value of 3 is 3. So this is the first number. And second number, you get 1 plus a max. Then this time, you do not do addition. You just get each of them. So you get 5, 9, and 3. Okay, so this max, the 5 plus 9 is a 14, plus 3 is a 17. This max is 17. This max is 1 plus it. The max is 9. 1 plus 9 is 10. Okay, so you have one number 17, one number 10. You're going to choose the smaller of those two numbers. Okay, the smaller of those two numbers. So this one is smaller. So m is equal to 10. Okay, so that is the bounds on the zeros. Let's see the other one. G of x is equal to 4 times x to 5 minus 2x cubed and plus 2x squared and plus 1. Okay, so first of all, you cannot directly apply the theorem for this polynomial function. The reason is that the leading coefficient is not 1. Because since it's not equal to 1, we factor out the leading coefficient. When we factor it out, all other terms, coefficient will be divided by 4. So this is factorization. And now you can see that the 0 of g is also the 0 of this new polynomial functions. Okay, the 0 of g is also the 0 of this new polynomial function because 4 does not contribute any zeros. Okay, so we are going to apply the theorem to this new polynomial. For this new polynomial, let's again compute those two max numbers. You have 1, you have 1 over 4, plus ops value is always ops value. So basically, you just ignore the sign. And the other one is 1 plus a max 1/2, 1/2, 1 over 4. Again, it's always ops value, no negatives. So this is equal to max 1. It's a 1 and 1 over 4. It's a 5 over 4. Here it's a 1. Half 1 over 4 is 1 over 4. So this is a 5 over 4. This is a 3 over 2. Which one is smaller? This one is smaller. So m is equal to 5 over 4. 3 over 2 is bigger, 5 over 4 is smaller. It's a $1.25. This is a $1.50. Right? Okay, so that's an application. This property is not very tricky. You just memorize the formula correctly. That's the important part. If you memorize it in the wrong way, you are not able to get the right answer. So just memorize this formula in the correct way. And don't forget, you must factor out the additional coefficient if the leading coefficient is not 1. Okay? Okay, so that's bounds on the zeros. The last one. Intermediate value theorem. Intermediate value theorem. So what is the intermediate value theorem? Is the following. For example, assume you have a continuous graph. Do you remember what is the geometric meaning of a continuous graph? You just sketch the graph without breaking it without breaking it. You sketch the graph without breaking it. Okay, so assume you have a continuous graph and one endpoint is below the x-axis, the other endpoint is above x-axis. And then definitely your graph will intersect x-axis at a certain point, which we just know it exists, but we don't know how to find it. And this C gave you y value 0. Fc is equal to 0. So C is a real 0. Okay, so that's basically what intermediate value theorem says. Okay, that's IVT, intermediate value theorem. Okay, so let f be a polynomial function if a is less than b, so you have domain, and if fa and fb are of opposite signs. Are of opposite sign. So one is positive, the other one is negative, or one is negative, the other one is positive. So this way. It doesn't matter. You always cross x-axis. Okay. If they are of opposite sign, there is at least one real 0 of f between a and b. So basically you have to cross x-axis once. You may cross it many times. For example, so here you cross it 3 times. Oh, sorry, this is not AB. Here's AB. This is FB. It's a FA. Okay. So at least once. And what is the assumption? The assumption just means you have a polynomial, and those two values on two sides of x-axis. Okay, a polynomial and two values on two sides of x-axis. Then you have a 0 between them. Okay, so that's IVT. Be careful. This theorem is one of the most important theorem in the calculus. So you will study this theorem again in the calculus. It's very, very important and useful. Pay attention to it. IVT. And IVT is a universal name for this theorem. We also have a lot of theorems with name, like the factor theorem, some zero theorem, remainder theorem. Those theorems, they have names in this textbook. They may have different name in another textbook, but IVT is always called IVT. Okay. Okay, example. Show that fx x to 5 minus x cubed minus 1 has a 0 between 1 and 2. Okay, so we are going to confirm that there is a 0 between some two numbers. Okay, so we will apply IVT. In order to apply IVT, we need a polynomial. Good. We need a 2-point AB. Good. We also need to verify FA, FB have different sign. Okay, what is FA? F1. F1, let's check. It's 1 minus 1 minus 1. It's negative 1. The sign is negative. Then F2. F2 is 2 to 5 minus 2 cubed minus 1. 2 to 5 is 32. 2 cubed is 8. It's 23. Positive, okay? So these two values are of opposite sign. Then by IVT, intermediate value theorem, there is a real 0 between 1 and 2. And that's it. That's it. You don't need to go into the IVT. IVT is like a black box. You just know once I satisfy the condition, then I will get a result. But you don't need to know why you have something inside it, how it works inside the black box. Technically, the black box works like this. One is on top, one is on bottom. When you cross it, there is a solution. But don't worry. You just examine polynomial, two numbers, different sign, then there is a 0 between them. Right? Let's see another example. Use IVT to show that fx equal to x to 4 plus 8x cubed minus x squared plus 2 has a 0 between -1 and 0. Okay. Well, you have polynomial. You have a and b. So what you really need to do is to evaluate the function at a and b and check if they have different sign or not. Let's check f-1. F-1, this is 1 minus 8. -1 cubed is negative. Times 8 is negative 8. Minus 1 and plus 2. Okay? So it's a 6. -6. Am I right? Yes, -6. And f of 0. F of 0, 0, 0, 0, f of 0 is 2. So you see here you have a negative sign, positive sign. They are of opposite signs. Then by IVT, fx has a real 0 between -1 and 0. Okay, so that's it. That is the IVT. That is IVT. Do the exercise and make sure you understand and handle the steps. So the section, this section 5.5 is very long. It contains a lot of stuffs, and some part they are connected tightly. Some part they are scattered. It's not that related. So you have to do exercise and so that you can memorize those properties. Okay. So if you have a question, send me email. I stop this video, and next we will study the fundamental theorem of algebra related to the complex zeros. So here we always talk about the real zero. In the complex zeros, something different appears. Okay, I stop it and open a new video quickly. Thank you.